students, in today's lecture we will discuss the atomic bonding in solids. So in your college physics or college chemistry class, you probably already learned the electronic structure or atomic physics basics. And in this class, in the lecture series of Material Science Engineering Fundamentals, we'll just directly jump to the chemical bonding interactions in materials. So probably you all know that when the two items are close to each other, they may repulse or attract each other based on the interatomic spacing. And there is, so this is a potential energy between the two items. And there is an equilibrium position where in the potential energy curve it corresponds to a minimum where the atomic are at their equilibrium state. So this is called equilibrium interatomic spacing. And corresponding to this energy curve, you will have this force curve where you have a zero force between the items at the equilibrium interatomic spacing, while when the items are pulled apart beyond this equilibrium interatomic spacing, they will attract each other. And when they are so closer than this interatomic spacing, they will kind of repulse each other. So they don't like each other. So this is the interatomic force, and this will give rise to your interatomic chemical bonding. Okay, so the bonding energy represents the energy required to separate the two items to an infinite separation. So to pull them far apart to each other. And this really depends on the electronic structure of your items. So there are essentially two types of chemical interaction between items and molecules. And this first type is called primary or chemical bonds, which include ionic bonds, covalent bonds, and metallic bonds, which are relatively stronger. The second type is really called secondary. It's called secondary bonds or physical bonds, which is based on the interaction between dipoles, electronic dipoles. And they can be divided into van der Waals bond and hydrogen bonding. And now we will look at these different chemical or physical interactions one by one. So before we jump into each specific chemical or physical interaction, we will look at the interatomic bonding energy of these bonds. And you can see that for ionic and covalent bonds, their interaction energy is usually higher, which means the bonding is usually stronger. And metallic bonding is usually weaker than the covalent and ionic bonds, but are much stronger than the secondary physical interactions of van der Waals bonds and hydrogen bonds. Okay. Another important concept is bond length, right? For primary bonds, the bond length or the equilibrium interatomic spacing is usually smaller, and for secondary bonds, this equilibrium interatomic spacing is usually bigger. Okay, so for stronger bonds or for primary bonds, you will have thinner distance or smaller distance between the two items, and also the energy well or the energy minimum is deeper. Okay, so the first type of bonding we are looking at in detail is the ionic bonding. And this can be exemplified by this simple sodium chloride crystal, right? You probably already know from your high school chemistry that the formation of the sodium chloride crystal is by this sodium atom giving up one electron to this chloride atom. So the sodium atom forms this so-called cation, okay, which is positively charged, and this chloride particle is becoming an anion, which is negatively charged. So the ionic bonding is usually formed between your metal and non-metal element, so that there is a complete transfer of electrons. And the result is the formation of these positively charged cations and negatively charged anions. And there are several characteristics of ionic bonds. The first is the electron transfers to form positive and negative ions. So it's a complete electron transfer. And the attraction comes from the Coulomb force between the positively and negatively charged ions. And the chemical bond is non-directional, which is the result of the fact that your transfer of electron is complete. So there's no kind of a free electron. And then the chemical bonding is so-called non-directional. The second type of specific chemical interaction is covalent bonds, which is formed by sharing of electron, usually between two non-metal elements. And in these elemental materials, for example, hydrogen, fluoride, or silicon, or diamond. And it is a so-called directional bonding because the share of the electron is only partial, right? So it's not a complete transfer like ionic bonds. And as a matter of fact, you can even calculate the so-called ionic character of your covalent bond, where it quantifies how much fraction of your electrons are shared in the covalent bond. Okay? The third type of primary bond for consideration is metallic bonding, where you have so-called free electrons. The outer shell electron is relatively free and it can be easily delocalized from the atomic radius, the atomic core, so that it will flow across the entire crystal of your metal, forming this so-called free electron gas, making the metal conductive. And this is actually found in all elemental metals. Okay? And here shows a table showing the bonding energies for metals. And you can see how the so-called free electrons are bonded to your core items. So now we move on to secondary bonding. And the first one is the van der Waals bonds, which is actually the physical interaction between your dipoles or electronic dipoles. The reason is that for some reason, you will have a separation of your positively charged particle and your negatively charged particle. So that usually happens in a molecule, right? So the center of your positive charge and negative charge, they are not coincide with each other and forming these dipoles. And van der Waals bonds is the interaction between these dipoles. For example, you have one dipole here, you have another dipole here, and they will kind of interact with each other by this pure physical interaction. And you can even have different types of van der Waals typed interactions based on how this dipole is formed. Okay? A special case in the physical bonding is the so-called hydrogen bonding, where you have this highly positively charged hydrogen atom exposing to a neighboring molecule, so that, for example, you have a HF molecule here, and this hydrogen atom is attracted by this fluoride atom, so that their interaction becomes a hydrogen bonding, and the interaction is fairly strong. Okay? And you may have different types of chemical and physical interactions in a single material. For example, in the case of graphite or in the case of boron nitride, right? You may have different chemical and physical interactions in the layer and between the layers. In particular, for something called graphite, which are pure carbon essentially, in the layer, the carbon atoms are forming this hexagonal shaped arrangement. And the interaction between the carbon atoms in the layer is covalent, which are strong. And you have a lot of layers. And the chemical interactions between the layers is actually van der Waals, which are really weak. So you have a strong bonding in the layer, and you have a weak bonding across the layer. A similar stuff is here. When you have a boron nitride crystal, you will have a strong interaction in the layer, and you have a weak van der Waals interaction between the layers. So the bonding characteristics and properties, they are strongly relevant with the melting and boiling temperatures, right? The boiling and melting phenomenon is actually represented by its chemical bonding strength. And in primary bonds category, the covalent ionic bonds are generally stronger than metallic bonds. And thermal and electronic properties depends on the free electron cloud, especially in metals. And the mechanical properties of solids depends on strings of bonds as well as the directional feature, okay, or the crystal structure. And this will be covered in our chapters on mechanical properties. So today we have studied the atomic bonding in materials. Thank you very much.